Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad, India. Today we are going to discuss about solve some of the problems on bending stresses on unsymmetrical sections. The course outcome of this topic related to the number of course outcome number is 4, and the course outcome here it is the mention. Apply the knowledge of theories of failure, shear force and bending moment relations for analyzing the flexural stresses, shear stress distributions and the failure of beam sections, and the Bloom's taxonomy related to the level, that is apply level. Now, what is the problem here? We are going to take some of the problems of unsymmetrical sections. But here the problem is here mainly focused on some of the problems. Yes, we have to calculate at a section XX. We have to calculate the maximum tensile and compressive stress at section XX. Now, a simply supported beam of length 3 meters. A simply supported beam of length 3 meters carries a point load of 12 kilonewtons at a distance of 2 meters from the left support. Okay, at a distance of 2 meters. Yes, this 12 kilonewtons is subject at a distance of 2 meters from the left support. The distance is 2 meters from the left support. The cross section of the beam is shown in figure. That is a hollow rectangular section. Determine the maximum tensile and compressive stress at XX. Okay, we want at a cross section of section XX. At that cross section, what to be found? We have to find out the bending moment M. We have to be calculated. So the theory of pure bending is M by I equal to sigma by Y. So when it is subjected to the load of 12 kilonewtons, the beam will bend in this direction. The topmost 5 layers experience the compressive stress, and the bottommost 5 layers experience a tensile stress. So we want the compressive and tensile stress. For that, what to be found? We have to find out location of the neutral axis. For that, we need centroidal distance bar Y. From that central distance, we'll calculate the area moment of inertia I value. I and Y, after knowing that, we have to find out the bending moment. Then only we can find out the stress values. These values can be found. Whether it is tensile or compressive can be calculated after calculating the moment of inertia value and Y value and also moment of resistance value. So first you have to calculate bending moment. What is the bending moment at that section XX? Now first you have to find out the bending moment at a distance XX. How to calculate? By using the two equilibrium equations. When it is simply supported beam, suppose load is acting W. It is RA and RB because at point A and point B. What is the first equilibrium? That is RA plus RB, upward reaction, sum of upward reaction forces equal to downward. That is equation 1. The second equation, you have to take it as the moment equilibrium. Take moment in arbitrary point. Suppose sigma m about A equal to 0. Then W times the distance from point support A to the point load, line of action of the point load, and RB from reaction B towards the distance. Thus we can calculate the reactions at A and B. After that we have to go for the bending moment equations by using the sign conventions of the bending moment. So let us begin. Yes, RA plus RB and RA plus RB equal to the equation 1. What is the first equation? The first equation, RA plus RB equal to 12 kilonewtons. That is the 12. That is 12,000 newtons. RA plus RB equal to 12,000 newtons. Now next, take moments about point A. Then RB into 3 meters. Then 12 into, it is in clockwise, 12 into 3, 12 into 2 meters. From that, RB value is 8 kilonewtons. And we know that RA plus RB equal to 12 kilonewtons. Then we know the RB value from this equation, that is 8 kilonewtons. Then RA equal to 12 minus 8, 4 kilonewtons. So thus we calculated for RA value and also value of the B value. Now after knowing RA and RB values, we have to find out the moment about this XX. Then take the moment beam X section XX, that is 1.5 meters distance, RA into 1.5 meters. That is 4 into 1.5, that is 6 kilonewton meter. That means 6 into 10 power 6 Newton millimeter. That is 6 into 10 power 6 Newton millimeters. We are following to maintain the dimensional homogeneity, that is Newton millimeters. Now M value we know. This is the value of moment resistance. But we have to find out location of the neutral axis. It comes how to calculate again. For a hollow section, the neutral axis, position of the neutral axis of the beam obtained by using the formula of that is A1 Y1 minus A2 Y2 by A1 minus A2. This is the formula for a hollow section. For solid sections, suppose for T section is there, the section 1 and section 2. What is the bar by formula? A1 Y1 plus A2 Y2 by A1 plus A2. But here it is the hollow section, A1 Y1 minus A2 Y2 by A1 minus A2. Then hatching section of centroid will come. Okay. Now what is A1? A1 is outer section area. That is 150 millimeters times 100 millimeter. That is A1. A1 equal to, how to calculate A1? Let's follow the table. A1 Y1. A2, you can follow another manner. Yes. A1 Y1, A2 Y2. What is the A1? For section 1, 100 into 150. What is the Y1? That is 150 by 2. 150 by 2. What is A2? Hollow inside section. That is 75 times 50. What is the Y2 distance? Distance of here. That is 50 plus 75 by 2. This is the value of A1. It is 75 Y1 and it is Y2 A2 and it is Y2. A1 Y1 minus A2 Y2 by A1 minus A2. What is the A1 value? 150 times 100 minus A1 minus A2. The value here it is obtained bar by 70.83 millimeters. So it is the 70.83 millimeters from the bottommost layer. That is from bottom edge, the location of the neutral axis. The location of the neutral axis here it is from bottom. How much distance? 70.83 millimeters. If you want topmost layer, what is the distance? The total distance minus 70.83. The total distance is how much? 150 millimeters. 150 millimeter. 150 minus 70.83. That is the centroidal distance. That is the neutral axis. From neutral, that is 150 minus 70.83. That comes as 79.17 millimeter. 79.17 millimeter from the topmost layer, and the distance from bottommost layer here it is 70.83. When the beam is simply supported beam subjected to point load, the topmost layer experiences what? Compressive stress. And the bottommost layer experiences tensile stress. Now, for in the case of sigma t prime, yt equal to m by I. What is the yt here? The distance of yt is 70.83. Okay, and in the case of sigma c by yc, that m by I, this yc becomes what? That yc is the compressive stress experience, that is 79.83 millimeter. So we calculated here location of the neutral axis means the distance from topmost fiber and bottommost fiber. We got to know it. And very important thing here it is, one more thing, you have to find out I value. What is the I value here? I equal to I1 minus I2. This is I equal to I1 minus I2. For hollow section, what is I1? Moment of inertia of outer rectangle, that is about neutral axis. That neutral axis, that is moment of inertia of the rectangle, that is 100 into 150 about its centroid plus A1 times distance of its CG from neutral axis whole square. What is 100 into 150 cube by 12? BD cube by 12. Outer capital BD cube by 12 time plus area 100 into 150. This is bar y minus y1 whole square. Then the A1 value we got to know. The value of the I1 value it is 28385833.5 millimeter per 4. And I2, this is the hollow inner section, inner rectangle we want. This I2 comes. What is that I2 comes here? Again, individual moment of inertia about its centroidal axis, that is BD cube by 12, 50, what is the D cube? 75 cube by 12. 50 times 75 cube by 12 plus B1 into D1, that is 50 into 75. Now we want a distance from neutral axis about this, that is 50 plus 75 by 2 minus 70.83 whole square. This is the value of I2. And the subtraction of, we have to subtract outer rectangle minus inner rectangle, then hollowness comes, that is I1 minus I2. Then I1 minus I2 moment of inertia, that is the total moment of inertia of this hollow rectangular section, that is 2558597.63 millimeter per 4. So now this I value we got to know, and Y value. Now here it is, the bottom edges, bottom edge will be subjected to tensile stress, and whereas the top edge will be subjected to compressive stress. So the top edge is at a distance of 79.17 millimeters, and the bottom edge is at a distance of 70.83 millimeters from neutral axis. These are 70.83. Yes, the bottom edge is subjected to whatever was the tensile stress. So for tensile stress, bottom edge, this is the Y value for tensile stress, and this is the Y value for compressive stress, because top edge is the YC and YT. The next step is we need M value, or if we know the M, how we have calculated M, already calculated. The relation, we know the relation of pure bending, that is M by I equal to sigma by Y. M by I equal to sigma by Y. We know the M value, moment of resistance. Sigma to be calculated, sigma equal to M by I times Y. What is the M value here? 6 into 10 power 6. I value we know. And Y back comes tensile stress. For tensile stress, I equal to from the bottommost layer distance. Yes, from bottommost layer distance. That is YT, 70.83. Tensile stress. Bottommost layer experience. The bottommost layer experiences tensile stress. Okay. So that distance, then 16.60 Newton per square millimeter. And we want compressive stress, then y value becomes distance from neutral axis to topmost fiber, topmost edge. That edge is experiencing compressive stress. That's why y becomes from neutral axis to the topmost distance, that is 79.17 millimeter. M by I into y, this y becomes value, then it is 18.56 Newton per square millimeter. So now here it is, M by I is remains the same for both. But what is variable here? Y is varying. So the stress value is proportional to the y. If the y value is larger, the stress value becomes larger. In this here it is, the tensile stress Yt is smaller than the compressive stress Yc. That's why sigma T is smaller than sigma C. The sigma T value, that is 16.6 Newton per square millimeter, smaller value in comparison to the compressive stress. Here the tensile stress is smaller value or less than the compressive stress value. Why here it is happening like that? Why compressive? Yeah, tensile stress value smaller than compressive stress. Because the compressive stress is experiencing direct load, whereas the tensile stress is the topmost fiber. That is reduction for tensile stress. Here it is the percentage. It is almost, it is around 2, not only percentage here, approximately it is 2 Newton per square millimeters difference. Yes. Now this is a calculation of the compressive and tensile stresses. Now, if you want to find out the stresses values, not only the value of the stress is dependent on the distance of neutral axis from the topmost fiber or bottommost fibers. Now, if you want to find out, know the strength of the section. The strength of the section is here. It is strength of the section represents here section modulus. What is the section modulus? So that section modulus is nothing but Z equal to I by Y. I by Y max. This is in mathematical relation. So the concept of section modulus, that is M equal to M by I equal to sigma by Y. Okay. So M by I equal to sigma by Y. From this, M equal to sigma times I by Y. Sigma becomes sigma max when Y becomes Y maximum. Then M equal to sigma maximum times Z. For a given stress, the maximum moment of resistance is dependent upon section modulus. If section modulus is higher, then the moment of resistance becomes higher. Thus, section modulus represents the strength of the section. So, if greater the section modulus, the strength of the section, the stronger will be the section. So, that is the meaning of section. That is the physical significance of section modulus. Now, how to calculate the section modulus of the sections? Suppose here it is. So the relation from section modulus comes I by Y maximum. That is sigma equal to M by Z, or M equal to sigma times Z. Now, there are three sections are here. One is square, another one is rectangle, and the third one is the circle. So we are going to find out the weight ratios of circular and rectangular beams with respect to circular and rectangular beams with respect to square beams. How to find out the ratios of the weights, and this problem value indicates the application of section modulus. of strength of the sections of beams. Let us let us read. Three beams have the same length, same allowable bending stress. Sigma is same, L is same, and the same bending moment M. The cross sections of the beams are square, rectangle with twice the width, and a circle. Rectangle with the depth twice the width. Okay, twice the width. B means it becomes 2B, and a circle. Find the ratios of weights of a circular and rectangular with respect to square beams. What is that ratio? Now here, X is the square beam. Both the sides, all sides are equal. Where B is the width of the rectangular beam and the depth of the rectangular beam, here it is equal to 2B. And where D is the diameter of circular cross section. We know the formula of moment of resistance having a relation between moment of resistance, bending stress and section modulus, that is M equal to sigma times Z. Where here Z is the section modulus. The condition, when here it is given M is the same and sigma is same, because M means the bending moment is same. Sigma, what is the sigma? Bending stress, allowable bending stress is same. But therefore, the section modulus, if sigma and M is same, sigma same, means what happens? Section modulus, it must be equal. That is the condition. Now, what is the section modulus? I by Y maximum. What is the I value for square beam? B dq by 12 by d by 2. What is the B and D here? It is x only. That is x into x cube by 12 times d by 2, that is x by 2. Then it what happens? X square by 6. That is section modulus, x square by 6. And next one, section modulus of rectangular beam. The section modulus of rectangular beam, again I by Y maximum, where I is the B dq by 12. What is the B value? B, D value 2B. B into 2B cube by 12, or D by 2, that is 2B by 2. After simplifying and cancelling the B and the numericals getting cancelled, the value of the section modulus is calculated as 2/3 of B cube. The third one, that is a circular section. The circular section, I value becomes pi d power 4 by 64, whereas Y maximum becomes d by 2. After substitution, it becomes pi d cube by 32. That is pi d4 by 64, 2 by d, d gets cancelled, d cube, and 2 to 32 times, then it is pi d cube by 32. So the section modulus of rectangular, this is the section modulus of square, and it is the section modulus of circle. These are the values observed. Now here, the equating the circular section modulus of circular section with the square section and section modulus of square rectangular section with the square section. How to equate it? This is the rectangular beam. Square is x cube by 6 and rectangular beam it is what is the square beam? Square and rectangular, that is 2/3 by 2/3 B cube. Because why we are equating with the square section? Because it is asked here, it is find the weight ratios of circular and rectangular with respect to reference. What is the normalizing reference? Square beam. That's why square beam section modulus equal to circular and square beam section modulus equal to rectangular beam. That's what we are doing here. The square beam section modulus is x square by 6. X square, okay, x cube by 6. X cube by 6 and rectangular beam is 2/3 B cube. Then B and X relationship. The B and X relation, that is 0.63 times X. And next, square beam section modulus is x cube by 6 and circular beam section modulus is pi d cube by 32. From this relationship, we can know the relation between D and X. that is D equal to 1.1927x. Now we need weight ratios. The weights of the beams are proportional to their cross-sectional areas. The weights of the beams are proportional to their cross-sectional areas. That's why what we did, weight of rectangular beam by weight of square beam equal to area of rectangular beam by area of square beam. The area of rectangular beam B into 2B by the area of square beam x into x. We know the B and x value. What is the B equal to? Just now we got it. B equal to 0.63 times x. Substitute here in the place of B 0.63 times x 2 times, and x get cancelled. That is the weight ratio. The weight of the rectangular beam with the square beam is 0.7938. Next, next is that weight of circular beam to the weight of square beam. What is the weight of circular beam? That is pi r square or pi d square by 4. And the area of square beam, it is proportional to the area. Area of square beam is x square. Now we know the D and x relationship. What is the D and x? 1.1927x. In the place of D, substitute 1.1927x whole square. Then make it calculation. Then what will happen here? It is x square and x square. Still x comes. That x, that value becomes D equal to x times, no, this is pi times, this is the pi times 1.1927x whole square. Then x square get cancelled, the numerical digit becomes 1.1172. That means here weight of circular beam is equal to 1.1172 times weight of square beam. So the circular beam weight is 1.1172 times more than W as the weight of the square beam. And from above value, equation 1, suppose if we consider equation 2. From equation, weight of rectangular beam RB equal to how much times? 0.79 times 38 times weight of rectangular beam RB. That means here it is the weight of rectangular beam. Weight of rectangular beam is the square beam only. Square beam. So it is less than one value. The weight of circular beam, it is more. The weight of circular beam is more than the weight of rectangular beam. That is in relation to the square beam. They want in relation to that. So if we understand that weight of circular beam is more, weight is more higher than here, it is 1.1172 times square beam. Whereas weight of rectangular beam, here it is 79.79 times, that is 79% of weight of square beam. It is more than, that is 111% more compared to square beam. Okay, so that means in relation to all this, which beam is more weight? So weight of circular beam is more, provided conditions that bending stress is same and moment of resistance is the same for this case study. Now in this problem, we have covered, summarized, let me summarize. What is the strength? What is the strength of the section? The strength of the section represents the mechanical parameter of section modulus. And section modulus is the ratio of moment of inertia to the Y max, I by Y. M by Z, Z equal to I by Y maximum. If we consider Y, how it represents, when Z is maximum, the moment of resistance maximum. Moment of resistance maximum, that means resistance to bend is maximum. Resistance to bend for the applied load, more resistance. It is more resistance represents the section mod. That means Z represents the strength of a section. So that section modulus we have studied for rectangular, square, rectangular and circular cross sections. And we found here in this problem, through this problem, the weight ratios of circular and rectangular beams with respect to square beams, and proved that, and we got to know by from this conclusion is that the weight of circular beam is 111%, 1.272% more than weight of square beam, and weight of rectangular beam is 79.38% more, 70% times that the weight of square beam. So in this section we have followed references and textbooks and web references that here are Subramaniam and Ramamritam, and also Robert Asaro, Lado Labada, and web references are nptl.ac.in. These are the references we followed for this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.